are going to continue with exercise 13, which reads: a rectangular coil consists of A equal to 100 closed wrapped turns and has dimensions A equal to 0.400 meters and B equal to 0.300 meters. A coil is hinged along the y-axis and makes an angle equal to 30 degrees with the x-axis. You have been asked to see the description in the figure. Now the A part of the equation is asking us to find the magnitude of the torque exerted on the coil by a uniform magnetic field strength is directed along the x-axis when the current is I, 1.20 amperes in the direction shown. We are going to see that in the diagram. The B part is asking us to find the expected direction of the rotation of the coil. So here is the figure that describes this question. So we begin with the A part, which is asking us to find the magnitude of the torque exerted on the coil. So the magnitude of the torque, first of all, is simply the magnetic moment, the cross product of the magnetic moment and the magnetic field strength. M is the magnetic moment vector and B0 is the magnetic field strength vector. So we need to determine the magnetic moment vector. So we can label our here is our rectangular coil. So we have O, we have A, we have B, and we have C. Now the directions, having the magnetic moment as Ni times my A0 vector, where A0 is simply the cross product of OA and OC. So it is the cross product of OA and AB, or the cross product of OA and OC, because AB is parallel to OC. So we need to find OA and OC. But before we find that, we are going to indicate the various directions. Vertically, that's the J direction for Y. Horizontally, for X, we have the I direction, and in this way we have the Z axis for the K direction. Now we need to find the vectors OA, the position vectors OA and OC. Now clearly we can see that the vector OA is simply 0.4J because it is directly on the y-axis, therefore the x and z coordinates are 0. Now we need to find the vector OC, that is the description. Where does this point C lies? Now we can see that this makes an angle of 30 degrees with the x-axis. So with that we can describe the coordinates of this point as now you see the y coordinate is going to be 0 because it is in the plane, it is in this plane down here. Because if you try to draw something like this, let's say we try to draw something like this, yes, so we try to, just that the way the z axis in the diagram was is not really good. So we try to draw something like this. So we see that this point has only the x because this is parallel to the x, so we have I, and this is parallel to the z, so we have here K. Alright, so from there we can describe the coordinates of this point C. Since there is no y coordinate, the y coordinate is going to be 0. Now the x coordinate, we can use the Pythagorean theorem to get it. So we need this distance, which is the adjacent of this right angle triangle. So with that, if we use this cosine of 30, we have adjacent on hypotenuse. The hypotenuse is 0.3. So we get this x coordinate to be 0.3, the cosine of 30. Now the direction is the I. Since there is no y direction, then it is 0. Now the z direction, we can use the sine to get this height. So the sine of 30 is the opposite, which is the height on the hypotenuse. So we get the height to be 0.3, the sine of 30, but it is in the z direction. So we have the unit vector in that direction to be k. So having that in mind, we have gotten our position vectors OA and OC. Now we do the cross product, so we have 0.4g, the cross product with cosine of 30 is root 3 on 2 times 0.3i plus 0.3 times the sine of 30 is half times k. Now we can do that in the determinant form. We get this result as the vector a 0. So with that, since they are vectors, remember I is a unit vector, so it should be bold. Now we need the magnetic moment, which is Ni times our vector A. This is our vector A. Now our N is the number of turns, which is 100, and our I is a current, which is 1.2. So multiplying, we get 100 times 1.2 times all of this, and we get 7.2I minus 12.36K approximately. Now from there we can get our third vector, which is this expression. But we're being told that the uniform magnetic field B has a value of this, and it is directed along the x-axis. It means that the y and z coordinates will be 0. So we can get the vector as simply 0.8 times I. So from there we get the magnetic moment cos 0.8I, because this guy is directed along the x-axis. We also use the determinant, and we get negative 9.888 Newton meter, and in the j direction. So the magnitude is simply 9.888 because we take the square root of this quantity squared. So we square this quantity and we take the square root, you just get 9.88. Now the second part of the equation is asking us the expected direction of the rotation of the coil. Now we see that the torque is negative, it's in a negative y direction, so it is going to be around here, so the negative y direction. So with that, the coil is going to be rotating in this direction. So let me indicate it in the diagram. So the torque is going to be rotating in this direction.